Here I have a high resolution image. The image is nearly 2000 pixels wide and around 1600 pixels tall. Let's say I wanted to produce a smaller version of this image, perhaps a thumbnail image. We want to reduce its size. So perhaps the simplest way to go about doing this is to just select every nth pixel in each row and in each column. And I could do that very simply with this MATLAB command here. I'm going to take every 7th pixel in the horizontal direction and every 7th pixel in the vertical direction. And the result is a much smaller image. This image is only 260 something pixels wide and 220 something pixels tall. This is a process that's known as image decimation. Very, very simple to compute. But you'll notice that there are some artifacts in this image. The tiled roof that we see very clearly in the left-hand image has resulted in a very strange pattern in the right-hand image. We can see that that regular texture of the tiled roof has disappeared and been replaced by some rather obvious lines which don't actually exist in the input image. So this is an artifact that's been introduced into the output image by the process of decimation, and the root cause of this is a phenomenon known as aliasing. The simplest way to think about aliasing is in terms of a one-dimensional image intensity profile. So let's imagine that we've drawn a line across an image, and this is the intensity profile, and it varies between plus and -1 in this particular case, and the horizontal axis is scaled in terms of units of pixels. So we can see some quite high frequency variation of the image intensity as we move across the profile. Now let's imagine that I sample this profile at every second pixel. So it's a sample at pixel 0, a sample at pixel 2, at pixel 4, and so on. Now, given that I have made these samples shown here by the black dots, I could also consider that the blue curve that's shown here is an equally good explanation of the values that I've measured at these 6 sample points. This is all based on a really important theorem from signal processing called the Nyquist sampling theorem. In this particular case, our sampling interval is 2 pixels. We've chosen our samples to be every second pixel. And that means that any signal that's got a period less than twice that, so any signal with a period that's less than 4 pixels will be aliased. It will be confused with a low frequency signal after we have sampled. The way to eliminate this aliasing problem is to remove the high frequency components from the image. And we've talked before about how we can use a Gaussian kernel to blur an image. And perhaps it's been unintuitive why we would ever want to blur an image. We go to so much trouble to make our images sharp and crisp and nice to look at. But convolving with the Gaussian kernel will remove these problematic high-frequency components. So in order to properly subsample an image, what we need to do is to apply a Gaussian kernel and then subsample or decimate. These two steps are done together in the toolbox function iScale. So the iScale function, we pass in our high resolution input image and we pass in the scale factor. In this case, I want the image to be 1/7 the size of the input image. The result will be the low resolution image shown here on the right. Notice now that those artifacts due to aliasing have been eliminated.